Hello everyone, and thank you for your interest in today's presentation about the BFS project or Back from Space. I'm Christian Pieronne, working as project lead at eNOVA Aerospace, a French startup based in Cannes, working on green space and new space applications, both in the software side for mission management, as well as on the hardware side, which is today's topic. Over the course of the next 15 minutes or so, I will present you more about what the BFS project is, what its objectives are, the context behind the project, as well as what the status of the current project is. So let's first take a look at the context of atmospheric reentry kits. Over the last couple of years, there has been an increasing amount of products that needed to be brought back to the surface. Those products include scientific samples, such as asteroid samples or experiments done in orbit, as well as the new and developing in-orbit manufacturing on the industrial side. As this market is really developing and increasing interest, some organizations such as NASA have begun to develop their own project as the HIAD that you can see on the picture on the screen. So now let's take a look more specifically at the BFS project that has been developed since 2020. So the BFS project started as an ESA-ITT in 2020 as a collaboration between eNOVA Aerospace, Nemesis, EFTH, and Nitrexo. This project then continued to answer the RNTs of CNES in 2021 and 2022, as well as the call for proposal in 2021 and 2022. So let's take a look at the potential uses for the BFS reentry kit. The BFS reentry kit can address scientific payloads or commercial payloads. On the scientific side, it aims to address small experiments as it is a Cubesat reentry kit, but has a lot of flexibility when it comes to the conditions or the need for human intervention. If human intervention is needed, the BFS can be launched from the ISS and re-enter from there, or if the experiment is autonomous, a rideshare is all that is needed. For the different conditions, we can either address suborbital flights as a rideshare or low Earth orbit in the ISS, as well as other conditions such as the radiation belts with a rideshare on a GTO orbit. On the commercial side, the main products that will be brought back by the BFS are products with a high added value. Those products can be either medical payloads, such as 3D printed organs or specific molecules that only develop in microgravity, or can act as a sort of courier for a space warehouse, giving quick access to any point on Earth. In addition, the production of different materials in space is currently developing and can be an interesting market for the BFS. On the business side of things, we are currently working towards a partnership with Nanoracks, as well as a partnership with Loft Orbital. So our partnership with Nanoracks aims to give their clients the possibility to bring their payloads back to Earth sooner than anticipated. Currently, when somebody sends a payload up to the ISS with Nanoracks, they have to wait at least 6 months before bringing back their experiment. Through our project, we aim to give the ability to bring it back whenever. 1 out of 3 clients of Nanoracks even said that I would be willing to pay more for this ability. Currently, our estimates with Nanoracks are that we could have 4 launches per year from the ISS, so the Bishop module that you can see on screen, as well as 4 launches from the Cygnus Spacecraft. On the side of Loft Orbital, the idea would be to expand their catalog by giving them a new capability that they don't have up until now, as well as give us access to more NEWSPACE customers. Finally, no matter with whom we work, our approach is always the same. We aim to be as cost efficient as possible. This means a compact solution, low volume, a rustic one, so with simple electronics, simple components, and technologies that are chosen to be as cost efficient as possible. So what would a nominal mission from the BFS look like? So for our nominal mission study, we decided to use an ISS launch as it is the most likely market that we'll address. Our reference spacecraft would be 4.5 kilograms with a 50 center diameter, modelized as a hollow sphere. The questions we take a look at are which landing site is the best, how much delta V is needed, what is our landing accuracy, and what are the mission requirements for an in-orbit demonstration. So first of all, we decided to look at which landing site is the best for an ISS return. We considered different candidates, such as the Woomera Range Complex in Australia, Utah Test and Training Range in the US, Las Perdenas Reales in Spain, Camp de Courgeoire in France, or the Sahara Desert in Algeria and Morocco. Our main factors were the orientation relative to the ISS, as the closer it was to the ISS trajectory, the less fuel we needed. In addition, our landing sites needed to be easily accessible to be able to retrieve our satellite without problem. So, after careful consideration, we decided to choose the Woomera Range Complex based on all those different factors. So now that we know where we're going to land, we'll take a look at the accuracy that is needed. To work on all those calculations, we decided to use Debrisk, a CNES software, to calculate all our reentry and simulate our trajectory through the atmosphere. The Woomera range allows us to have a downrange error of 235 kilometers. Using the parameters that you see on the right of the screen, we determined that the maximum allowed error in delta V for our deorbit burn was of 0.7 meters per second, which in turn led to a propulsion accuracy needed of more or less 0.1 meters per second. In addition, we calculated the worst case scenarios, which led us to the variations allowed that you see on the bottom right of the screen. With this being said, let's take a closer look at the mission specifications and requirements for the BFS. The nominal lifetime of a mission is 6 months, with maneuver capabilities needed up to 150 meters per second. In addition, as it is ISS launched, all the parts of this reentry kit have to be safety compliant with the standards on the ISS. For the in-orbit demonstration, we'll also need to be able to measure temperature, pressure, accelerations, as well as position and velocity inside of the spacecraft to be able to adapt later models. All this means that we also require a data link to the ground to be able to constantly transmit all the data that we are recording. So let's first take a look at the propulsion module that we chose. The main considerations were the thrust, the delta V at equivalent mass, as well as the power consumption. We need enough thrust so that the mission doesn't take too long, as well as a small power consumption and big delta V at equivalent mass to be able to conserve on power both on the tank as well as on the batteries. We considered 60 candidates on those different criteria, with the main ones coming out being the PM200 by Hyperion, with the characteristics shown on screen, the EPSS C1 by NanoAvionics, as well as different propulsions from Dawn Aerospace. On the electronic side, we need to make sure that all sensors and communication relays are connected to the onboard computer in a coherent manner. As such, we developed this diagram to show how the different sensors and interfaces are connected, both for the data link as well as the power transmission. So now let's take a look at the heat shield of the BFS reentry kit, as it is a core part of the kit protecting the payload during the atmospheric reentry. The biggest goal of the heat shield is, as the name implies, protect the payload from the heat generated during reentry. As such, we define the criteria as having the payload temperature always be underneath 60 degrees Celsius, as well as the internal side of the heat shield always underneath 600 degrees Celsius. For the different materials in this kit, we decided to choose the 3M Nextel 312 for the flexible thermal protection system, some multilayer isolation, so MLI, and for the payload, aluminum. We studied 3 cases to determine which one was the most demanding. The first case was a reentry during 60 seconds at 1500 degrees Celsius. The second one, a reentry during 300 seconds at 1000 degrees Celsius. And finally, a reentry during 700 seconds at 650 degrees Celsius. Through all this, our analysis showed that the most demanding case was the reentry at 1000 degrees Celsius during 300 seconds. This reentry meant that we needed an FTPS thickness of 3.6 millimeters, which in turn resulted of an internal phase temperature of 584 degrees Celsius. In addition, with an MLI thickness of 4 millimeters, we could guarantee that the payload temperature stayed at 58.9 degrees Celsius, thus respecting the constraints that we put at the beginning. Now let's take a look at the second big aspect of our reentry kit, the mechanical aspect. For the mechanical side, the maximum surface pressure we may face during reentry is 3400 pascals. As such, we chose to have 8 beams to hold our flexible thermal protection system in place, but still needed to design them to resist all this pressure. Those beams were chosen to be 300 millimeters long and made of nitinol alloy, a shed memory alloy, allowing us to deploy our FTPS when needed. For our constraints, we set our maximum tip displacement at 78 millimeters. After analysis, we found out that with a diameter of 6.5 millimeters, our beams allowed a 74 millimeter tip displacement, thus respecting our initial constraints. This led us to a mass of beam of 513 grams. So now let's take a look at the future of this project. This project has been submitted to the CNES Call for Proposal of 2022 with the objective of developing an in-orbit demonstration and in-orbit validation in 24 months. In addition, the study of the nanosat size has begun. This nanosat-sized reentry kit could address 2 different types of configuration, one of 5 Cubesats and one of 9 Cubesats. This allows more flexibility in the type of payloads addressed, as it can address bigger payloads with more complex shapes and not just one small cube. To develop this nanosat size as well to go more in detail with the Cubesat size, eNOVA has been in contact with many different potential partners. Among those partners, we can cite Mechanoide for the separation ring, or Dawn Aerospace for the propulsion. In addition, a request for information has been sent to different European platformists, such as NEWSPACE, Emeria, NanoAvionics, or Endurosat. So this concludes our presentation about the BFS project from eNOVA Aerospace. I hope that it was very informative and that you are interested in this project. If you have any more questions, feel free to ask them in the comments down below or email us. In addition, make sure to check out our website, eNOVA-aerospace.com, to learn more about our future projects. Thank you very much.